Hi there. Here's my solution for question 4.19. We're looking at mold growth. So on part A, we want to graph the average mold colony size against time. That's the first thing we want to do. So let's take a look at the calculator. I've already entered the data into list 1 and list 2. So we're going to look at, if I go into my plot number 1, I need to reset this. So I'm using list 1. That is time in terms of hours, my explanatory variable. And my response variable is the average colony size. That's in list 2. So we'll zoom 9 this. There we go. So clearly this is not a linear pattern. So next we're asked to graph the logarithm of the mean colony size against time. So you could use common logs. I'm going to go ahead and use natural logs. And the suggestion here is that this model should indeed be exponential. Take a look. Again, in an exponential model, if I take the log of both sides, the left side turns into the log of the response variable. So that would be the log of the average of the colony size. So on the right side, if I take this expression and split it up, I get the natural log of a, that becomes my constant, plus the value of x, that is the input, times the natural log of b, that ends up being the slope. So this really should be a linear form. So if indeed I think that this mold growth follows an exponential model, then as suggested by part A, if I graph the logarithm, so we're going to use natural logarithms of mean colony size, if I graph that against plane time, I should see a straight pattern. So let's take a look. We'll go to the home screen. First of all, I need to take the logarithm. You could use common logs or natural logs. I just tend to use natural logs. So I need to take the natural log of list 2. That is where the response variable lives. I'm going to store that into list 3. So now to create the graph suggested in part A, what I need to do is go in and leave list 1 alone. That's the plane x. That's the plane explanatory variable, which is time in hours. So my natural log of the mean colony size, that's in list 3. That's where I stored it. So we can zoom 9 this. And now we're already on to part B. Part B says that microbiologists divide the growth of mold colonies into 3 phases that follow each other in time, and exponential growth only occurs during one of these 3 phases. So I would offer that the exponential growth then in this picture should occur where we see the straight line relationship. So it looks like actually the size, the average colony size actually drops for a while. And then starting right about here, which if we trace this, we'll trace that in just a second, we see a relatively strong linear trend. But then this point here, which represents 36 hours, so it looks like we've fallen off of that linear trend. So if we trace this, here we go. So right here at 6 hours, this looks like a reasonable location for the start of exponential growth. And it looks like that continues through 9, 12, 15, 18, 21, and here at 24 hours. So the exponential portion of the growth for this mold colony looks like it happens from approximately 6 hours to approximately 24 hours. So finally then, in part C, our plan then is to create a model for this exponential period of growth. So we're supposed to just look at these from 6 hours to 24 hours, these value of the data, and then we're going to run a least squares regression there and fit a good model. So I'm going to go back to the data, stat enter. So here, I want to delete the entries in list 1 and list 2 and in list 3. The first 2 entries, those represent the data from 0 and 3 hours. So I need to be careful. I need to delete them from all 3 lists in order for my ordered pairs to remain consistent. And again, it looks like once we've passed 24 hours, at least the data for 36 hours suggests that we are in a different phase of mold growth. So I'm going to delete, again, from list 1 and list 2 and list 3, I'm going to delete the last observation. So now remaining in my lists 1, 2, and 3, I have just the data from 6 hours to 24 hours, and I am ready to fit the least squares regression line. So we'll hit the stat button, go to calculate, we'll go to option 8. So the X list needs to be plain X, that is stored in list 1. And the Y list needs to be the natural log of the response variable that is stored in list 3. Very good. We're ready to calculate the linear regression. After we calculate that, then I need to write that down. So we have an intercept of negative 1.37, and then we have a slope of about, let's call it 0.20. So I'm going to write that down here, and then we'll go look at the model. So the natural log of the mean colony size, which is estimated. So we have an intercept of negative 1.37, I'll call it, plus my slope, we'll call it 0.20 times x. So let's switch over then, so you can see what I'm writing here. So for question 4.19, this is the linear model that we just estimated. So the natural log of the response variable, which is a prediction, that is equal to the constant, negative 1.37, plus the slope of 0.20 times x. So notice above it, I put the exponential model. So again, that negative 1.37, that corresponds to the constant. That's the natural log of a. Here is the input of x. So the slope, the 0.20, that corresponds to the natural log of b. So that's how we took originally that exponential model and we rearranged it using x and the natural log of y. We rearranged it into a linear model. That's why question 4.19 is calling for you to build a linear model. There it is. So x here, this represents hours. So, and the natural log of y hat, so this predicted value for the natural log of y, this is the predicted natural log of the mean colony size. So, and now what the question asks you to do, it says to use this line to predict the size of a colony 10 hours after inoculation, so after the initiation of the colony. So if you wanted to, you could actually take this and turn it into the exponential model before you make your prediction, but there really isn't any need to do that. You can make your prediction straight from this linear model by substituting 10 in for hours. So to make my prediction, my predicted colony size is the negative 1.37 plus 0.20 times 10 hours here. So we're going to go ahead and substitute that into the calculator. So we need to go to the home screen here. Very good. So I've got my negative 1.37 plus 0.2 times 10. That gives me 0.63. So now that is not the prediction yet. Be careful. So what I have found is the predicted natural log of the mean colony size, and that's 0.63. So to actually make the prediction, I still need to convert this from log form into plain y. So if I rewrite this, remember a natural log is a log base e of y, and that's 0.63. So what I can really do then is take e, my base, to the power 0.63. That should equal my value of y, in this case my predicted y value. So we will take e to the power 0.63, and that will make our prediction for us. So second natural log button, put in 0.63. And there's our prediction. It looks like about 1.88. I don't know the units that they're using for average colony size here, so we'll just leave it as 1.88 for our prediction. There you go. That's actually what you're being asked to do. That's the prediction that you're being asked to make by using this linear model that we estimated way up here at the top. So it would be a little bit extra work. You're going to get a similar prediction, but if you really wanted to, you could create the exponential model from this linear model. This isn't necessary, but I'll show you how to do it in case you're curious. So if you wanted to do it this way, you could do the following. I know that the constant, the negative 1.37, that is the natural log of A. There it is. And I know that the slope, the 0.20, is the natural log of B. So I could find A and B and actually create this as an exponential model if I wanted to. So the natural log of A, that's negative 1.37. And then the natural log of B that I need to find, that's 0.20. So if I change both of these into exponential form, this says e to the power negative 1.37. That's going to be A. And this says e to the power 0.20. That's going to be equal to B. So I need to go to my calculator and I need to estimate each one of these. So second natural logarithm, e to the power negative 1.37. That gives me an A value of about, let's call it 0.25. And then for B, I have e to the power 0.20. So I'll take e to the power 0.2. That comes out to be approximately 1.22. So again, there isn't any reason that you have to do this, but if you wanted to rewrite that linear model as an exponential model, here it is. So my predicted mean colony size, my predicted response value, my y hat, is equal to the 0.25 times the base, 1.22, to the power x, where the explanatory variable is time. So again, I could find my prediction simply by substituting in the 10. Now we've rounded a little bit, so we're going to get a slightly different answer. That's just rounding error. So if I go to the calculator and type this in, my constant is 0.25, my base is 1.22, and I can raise that to the power 10, and that should give us approximately the same answer. There's 1.83 approximately. There's my prediction. And again, the difference here is rounding error. When I predicted using the linear model, I had 1.88, so we're pretty close. Hope this has been helpful. And again, one of the keys to remember here, what we're really doing here fundamentally, and I'll even review them both while I've got it right here, fundamentally, an exponential model is appropriate if, when you look at the data, you can build a linear model based on plane x and the natural log of y, the plane explanatory variable and the natural log of the response variable. If that's linear, an exponential model is appropriate. So again, reviewing, a power model then is appropriate if, when you do all of the transforming using logarithms, if the natural log of x and the natural log of y, so if the natural log of the explanatory and response variable, if those can be modeled with a linear model, then a power model is appropriate. Those are the two nonlinear models that you'll be expected to know in this unit and on the AP exam. Hope this has been helpful.